going to talk about connected sets. First, let's recap some ideas from before. Let's say that we have a family of open sets O sub lambda that are indexed by some set capital lambda. Given any subset S of the real numbers, we'll say that such a family is an open cover for S if S is contained in the union of these O sub lambdas. Next, let's say that capital theta is a subset of our indexing set capital lambda. We say that the collection of O sub lambdas, where the lambdas lie in capital theta, is a subcover for S if S is contained in the union of the O sub lambdas, where now lambda ranges in the subset capital theta. We'll say that this is a finite subcover if it is a cover, yet capital theta is a finite set. We'll give some examples. Let's say that S is the collection of real numbers. If we denote O sub lambda to be the open interval from lambda minus 1 to lambda plus 1 for any real number lambda, then we see that the collection of the O sub lambdas, where lambda ranges over the real numbers, is an open cover for S. Next, let's say that S is the open interval from A to B. If we denote O sub 1 as the same open interval, then the set containing O sub 1 is an open cover for S. In fact, this is a finite subcover. Finally, let's say that S is the union of the two closed intervals from 0 to 1 and from 2 to 5. If we denote O sub lambda to be the open interval from negative lambda to positive lambda for any natural number lambda, then we see that the collection of O sub lambdas, where lambda ranges over the natural numbers, is an open cover for S. In fact, we could simply take the set consisting of O sub 2, O sub 3, and O sub 6 to be a finite subcover for S. The following three statements are equivalent for subset S of the real numbers. First, every limit point of S is an element of S. Second, every Cauchy sequence, X sub n, contained in S has a limit also contained in S. Third, S is equal to its own closure. Any subset S satisfying any of these equivalent properties is said to be a closed set. The following are equivalent for subset K of the real numbers. Every sequence X sub n containing K has a convergent subsequence X sub capital N sub n where the limit is an element of K. Second, K is closed and bounded. Third, if there exists a family O sub lambda, where lambda ranges over some indexing set capital lambda, of open sets such that K is contained in the union of the O sub lambdas, then there is a finite capital theta contained in our indexing set capital lambda, such that K is a union over O sub lambdas, where lambdas lie in this finite set capital theta. This is what's typically called the Heine-Borel theorem. Any subset K satisfying either of these three equivalent definitions is said to be a compact set. Today we're going to start off the lesson by discussing what are called separated sets. We'll begin with the following result. Let's say that A and B are non-empty subsets. Then the following two statements are equivalent. First, the closure of A and B have no elements in common. The A and the closure of B also have no elements in common. That is, A bar intersect B equals A intersect B bar is the empty set, where A bar is the closure of A. Second, the intersection of A and B is the empty set. The intersection of the limit points of A and B is the empty set. And the intersection of A with the limit points of B is the empty set. Any pair of non-empty subsets A and B satisfying either of these two equivalent statements are said to be separated. A and B are said to be disjoint if A intersect B is the empty set. We mention this to say that being separated is a stronger condition than being disjoint, since we also require conditions on the limit points of A and B. Before we try to prove this theorem, let's go over some examples. Let's say that capital A is the open interval from lowercase a to lowercase b, and capital B is the open interval from lowercase b to lowercase c. Then A and B are disjoint because the intersection of A and B is the empty set. Moreover, the closure of A is the closed interval from lowercase a to lowercase b, and the closure of B is the closed interval from lowercase b to lowercase c. So in this case, we see that the limit points intersect B is the empty set, and A intersect the limit point of B is the empty set. This means that capital A and capital B are two separated sets. As another example, let's let capital A be the open interval from lowercase a to lowercase b, but capital B be the closed interval from lowercase b to lowercase c. Then A and B are disjoint because the intersection of capital A and capital B is the empty set. However, if we look at the limit points of A, that has an element in common with capital B, namely the point lowercase b. On the other hand, A intersect the limit points of B is the empty set, but we see that capital A and capital B are not separated. As a third example, let's consider a prime number P and consider the following two sets, capital A and capital B. Capital A intuitively is the set of all the elements, the rational numbers, to the left of the square root of P, and capital B is the set of rational numbers to the right of the square root of P. Then we see that A and B have no points in common, that is, A and B are disjoint. However, let's take a look at the limit points of capital A. This will be the collection of real numbers to the left of the square root of P, and the limit points of capital B will be the real numbers to the right of the square root of P. In particular, capital B has nothing in common with the limit points of capital A, and similarly, capital A has nothing in common with the limit points of capital B. So we see that these two sets, capital A and capital B, are indeed separated. We'll now prove the theorem. Let's make a couple of observations before we begin. First, recall that the closure of A, namely A bar, is the union of A and its limit points L of A. Second, the distributive law for sets says given any three sets, capital X, capital Y, and capital Z, that if we take the union of X and Y intersect with Z, that is the union of X intersect with Z and Y intersect with Z. In particular, if we consider the intersection of A bar with B, that is the union of A intersect B with limit points of A intersect B, and similarly, the intersection with A and B bar is the union of A intersect B with A intersect the limit points of B. Let's show that the first statement implies the second. Let's assume first that the intersection A bar with B and A with B bar is the empty set. Since the intersection A and B, the intersection L of A with B, and the intersection A with L of B are subsets of A bar intersect B union A intersect B bar, and this here is actually equal to the empty set, we see that each of these three, namely A intersect B, L of A intersect B, and A intersect L of B, must each be the empty sets. Conversely, let's say that these three intersections are the empty set, namely A intersect B, L of A intersect B, and A intersect L of B. Since A bar intersect B and A intersect B bar are subsets of the union of these three, A intersect B union, L of A intersect B union, A intersect L of B, and this union must be the empty set, we see that both A bar intersect B and A intersect B bar must both be the empty sets. Next, let's move on to the concept of connected sets. This is really the main topic for today. The following result is related to separated sets that we just considered. Let's say that capital S is a subset of the real numbers. Then the following three statements are equivalent. First, we cannot write S as the union of A and B for any separated sets A and B. Second, whenever we have a real number that's between lowercase a and lowercase b for some lowercase a, lowercase b in S, then this real number p must also be an element of S. Third, for any two non-empty subsets A and B satisfying S equals A union B and A intersect B is the empty set, then there exists a Cauchy sequence A sub n contained in capital A where the limit P is actually contained in capital B. Any subset S satisfying either of these equivalent statements is said to be connected. Otherwise, we say that a subset S is disconnected. That is, if S equals A union B for some separated sets A and B. We'll say that capital S is totally disconnected if, given two elements lowercase a and lowercase b in capital S, we can find separated sets capital A and capital B such that lowercase a is in capital A, lowercase b is in capital B, and capital S is the union of capital A and capital B. Before we try to prove this, let's go over some examples. First, let's say that capital S is the open interval from A to B. Well, if there's any real number P between A and B, then clearly P has to be an element of S. Then, by our definition, capital S is a connected set. Observe that really the same statement is true if we have the closed interval from A to B or the half open intervals from A to B. They must also be connected sets. Second, let's consider the union of two closed intervals from 0 to 1 and from 2 to 5. Then we can write S as A union B, where capital A is the closed interval from 0 to 1 and capital B is the closed interval from 2 to 5. In particular, capital A and capital B are separated sets. This shows that capital S is disconnected. Third, let's let S be the Cantor middle third set. Let's pick two Cantor numbers, lowercase a and lowercase b, such that A is less than B. Recall that we can write A in our ternary expansion as a sum a sub k over 3 to the k, and similarly we can write B as a ternary expansion, a sum b sub k over 3 to the k, where lowercase ak and bk have to either be 0 or 2. Since a is less than b, this means that a sub k is less than or equal to b sub k for every index k. However, since a does not equal to b, let's say for example that a sub n does not equal to b sub n. That means that a sub n is 0 while b sub n is equal to 2. So let's denote q to be as follows. The first n minus 1 elements in our sum will just be the elements that we have from a, the a sub k over 3 to the k. Remember that because k is less than n, we are also assuming that a sub k equals b sub k. Now let's let the next term in our ternary expansion be halfway between a sub n and b sub n. So it'll be 1 over 3 to the n. And then finally, the last remaining terms, let's just let to be the b sub k's. So we have a sum b sub k over 3 to the k. In particular, this element q is not a Cantor number. That's because of the 1 over 3 to the n. And q has to lie between a and b. Now, using this q, let's write the following sets, capital A and capital B. Capital A will just be those Cantor numbers to the left of q, and capital B will be those Cantor numbers to the right of q. We see now that the closures, A bar and B bar, have to lie in the closed sets from 0 to q and from q to 1, respectively. In particular, these two sets, capital A and capital B, satisfy three properties. First, lowercase a is in capital A, lowercase b is in capital B. Second, the entire set of Cantor numbers is the union of A and B. And third, the intersection A bar with B is the empty set, and the intersection with A with B bar is also the empty set. This actually means that the Cantor middle third set is a totally disconnected set. Now let's go over the proof of the theorem. Let's pick two numbers, a and b and s, where a is less than b. We're going to prove by contradiction that there must exist a P where P is between A and B. So let's assume that there is a P between A and B that is not an S. Similar to what we did with the Cantor sets, let's denote capital A as the set of elements in the set S to the left of P, and let's denote capital B as the set of elements in S to the right of P. Then we can actually see that A bar intersect B is the empty set, whereas A intersect B bar is the empty set. But because P is not an element of S, we then see that S has to be the union of a pair of separated sets A and B. But of course, this contradicts our assumption that property 1 holds, so we do see that property 2 does indeed hold. Next, let's prove that 2 implies 3. Let's choose any non-empty subsets A and B, satisfying S is the union of A and B, and A intersect B is the empty set. We're going to construct a Cauchy sequence of A sub n's contained in capital A, where the limit P lies in capital B. For the first part of our construction, let's pick any A0 in capital A and any B0 in capital B. Such elements exist because we're assuming that capital A and capital B are non-empty. Without loss of generality, let's say that A0 is less than B0. Then the second property implies that the closed interval K0 from A0 to B0 must be contained in capital S. Notice that K0 is a non-empty compact set, and we'll let capital L be the difference between B0 and A0. Recursively, we know that we can write K sub n as the union of closed intervals from an to bn, and then from bn to bn, where the midpoint here is p sub n. Now let's choose k sub n plus 1 as one of the halves of this interval, k sub n, that allows us to say a sub n plus 1 is in capital A, and b sub n plus 1 is in capital B. Explicitly, we'll construct it as follows. Again, let P sub n be the midpoint of our closed interval K sub n. That is, P sub n is A sub n plus B sub n over 2. Now, if P sub n is an element of A, we're going to choose the right half of the interval in K sub n. Namely, A sub n plus 1 is P sub n, and B sub n plus 1 is B sub n. On the other hand, if P sub n is in capital B, we'll choose the left half of this interval. Namely, A sub n plus 1 is A sub n, and B sub n plus 1 is P sub n. Notice that K sub n plus 1 is contained in K sub n, and it is, because a closed interval, a non-empty compact set. Observe that the difference B sub n plus 1 minus A sub n plus 1 inductively is just L over 2 to the n. So as n gets larger, we'll see that this quantity gets smaller and smaller. In the breakout groups today, we're going to show the following. Let's assume that we have a collection of non-empty compact sets where K sub n contains K sub n plus 1. Then K, which is the intersection, is also a non-empty compact set. In the case that we care about, this means that there exists some element P in this intersection K, but of course K is contained in S, and S we know is equal to the union of capital A and capital B. Without loss of generality, say that lowercase p is an element of capital B. In fact, because the distances between these endpoints, b sub n plus 1 minus a sub n plus 1, is equal to L over 2 to the n, we see that a sub n's and b sub n's get closer and closer together, and they have to end up at this point P that is in this intersection capital K. This means that the limit, as n increases without bound, of a sub n must be equal to P. But we've constructed now our Cauchy sequence, the a sub n's, in capital A, whose limit, namely P, is in capital B. This shows property 3. Now, to finish off the proof, we're going to show that property 3 implies property 1. By way of contradiction, let's say that actually we can write S as the union, capital A union capital B, for some separated sets, capital A and capital B. Since property 3 holds, this means that we can find a Cauchy sequence of A sub n's inside of capital A, where the limit P is inside of capital B. Since A intersect B is the empty set, this means that our limit P cannot be an element of capital A. But now let's be careful about what it means to be a Cauchy sequence. Given a positive epsilon, there exists a delta such that the absolute value of an minus p is less than epsilon whenever n is greater than delta. But another way to say this is that the a sub n's are an element of the open interval v sub epsilon of p intersect a, and a sub n does not equal to p. But by definition, this means that p is in a limit point of a, so p is an element of the closure a bar. But now we have a point that is an element of a bar, and it is an element of capital B. So a bar intersect B does not equal to the empty set, which contradicts the assumption that capital A and capital B are separated sets. This completes the proof. Thanks very much for watching.